So welcome back, everyone. So this is so a week where I get to enjoy being in so two virtual meetings at the same time. I'm supposed to also be doing this. I guess the good part of this is I actually get to be here to actually teach in person, but the bad part is I'm trying to balance kind of two virtual meetings across the globe at the same time, so I might be a little bit less organized than so typical. So we are here in the last content-based lecture of the semester. We're going to have one more lecture after this, that's just going to be like a review of everything. This lecture is going to kind of try and give an overview of the various types of other classifiers out there. We didn't quite put all the pieces together for kernel SVMs and SVMs in general. So we'll kind of start with this, and then we'll talk about some other kind of popular ones like neural nets, like decision trees, and etc. And so, you know, you're not going to become an expert in these at the end of this lecture, but you'll get a sense of what they are and how they work and how they fit in to everything else we've talked about in this course, and kind of, you know, give you a perspective on the breadth of the types of classifiers, and then some of the challenges in deciding, well, if I want to build a classifier, I don't just press a button and build a classifier. I have to make a decision on which one to use, and this decision is not always kind of obvious. So hopefully I'll give some insight to that, and where is kind of active research in like deep nets and like random forests, which will be basically extension or kind of bigger versions of the things we'll talk about in class today. Let me just quickly review. Yeah, so we are at the very end of the schedule. Quiz 6 is back. The class average on Quiz 6 was great. I'm hoping for a similar average on the final. That would be awesome. Again, the final will be, okay, our final date scheduled by the registrar's office was Friday, December 17th. This might be like the last day. It's supposed to overlap with 10:30 a.m. and to 12:30 p.m. During that time, I will be here in this room, and you can come here if you want a quiet place to take it. But it will be online. It will be a Canvas quiz, just like the quizzes. And you can, once you start, you have 2 hours to finish. I will be here to answer questions. I'll also be available on Zoom at that time, but you're welcome to take it from when it opens, I think Thursday evening before, until Friday late afternoon. I'll have it open. Okay, so that's the plan. The semester, we'll do a review on Thursday. It's the plan, and we'll probably I'll try and hit on a couple of topics I think that deserve a little bit more time, and then we'll try and go through as much as we can of the practice exam down here in the bottom right corner of the screen here. Okay, so that'll be the plan. If you go and you can practice and try and go through that before the class, that would be kind of a good thing to do. Otherwise, I'll be open to any questions, suggestions you have. And then homework 5 is due on Friday. I hope this is not an especially challenging homework, but try and get it done. It'll definitely be good if you finish it before you take the final, because it's a good way to practice all this stuff. Great. Yeah. Is the final going to be? Yeah. So right. There's a time window that's going to be, but I have a longer time window when you can take it. But that's, yeah. Great. I think I answered that. Okay. All right. So let's get. Oh, question. Yeah. So, you know, it's okay. They're so kind of two things about this. One, it's a Canvas quiz, and there's no way I can, like, morally, I think, at least enforce that that you don't use outside sources. Like, you know, a lot you're going to take at home, and I'm not going to use like the ProctorU source stuff, which is, I feel, an invasion of privacy, and there's other issues with that software so I think in all of computer science, we've kind of mostly agreed not to use that software. So there's no way I can check this. So you can use outside resources, but if I find out that you're talking with someone else and that sort of stuff is not okay. But you can find anything. What I suggest, and I think what will be the most useful for you, because notation changes so much in different areas, is anything linked off the web page is fine, including the full book. So it's open source, but if you don't know this stuff ahead of time, the 2 hours is not going to be long enough. Okay, so you should study, you should know it. It's such that if you know the material, it should be easy to complete in the 2 hours. If you don't know, it's going to be hard to learn it from the book in that time period. It will again have a cheat sheet. The cheat sheet now will be, I think you'll get 6 pages instead of 1 page. So they can so think of, it could be all of your cheat sheets for the whole semester just put together, but some of you may have realized, well, that cheat sheet wasn't that helpful, so you're going to review it and maybe make it over again. But if you turn that in, you will get the same. There'll be some similar allowance on the final, as we did on the quizzes. Yeah. Yeah. So don't talk to other people during the final. Don't message other people. Can tell you to do that. It's really hard to enforce that without doing it in a classroom, which has, anyways, this is, I think, the overall best option. There are other things there are other ways we're trying to enforce, I think cheating is an issue, and I don't want you to cheat. And if you do cheat, the consequences are way worse than getting a little bit lower score on your grade. And we have mechanisms in place to kind of check and prevent cheating. And I'm not going to tell you what all of those are, because then it makes it easier to kind of circumvent these things. But we do have some mechanisms in place. So, yeah. So, okay, great. So let's get on with the lecture. So we were talking about classifiers. And the input to a classifier is going to be a set XY, which is kind of a paired set. This is in RD cross minus plus. That means each XI is going to be in RD, and each YI is going to be paired, and it's going to be in a class, say, often -1 and +1. There are extensions with multi-class or other things we can think about. In this class, we'll just think about this binary sort of classifier. And the goal, and I'm going to try and write this generally here, but this is the classification problem. This is, right, and the goal is a function. Either we can write it as f of f, which goes from, and I'm going to write this generally today because we're going to be talking about general classifiers, from RD to minus plus, or G from RD to R. So we want that f of xi to basically match the y fi on as many xi yi as so possible, and or we could say that the sign of g of xi. Okay, we're talking a lot about where, it's hard. Fi is going to be this discrete function. It outputs something binary. It's hard to optimize that. So often, although we'll see some methods that directly go to today, that directly go to some binary function. They skip the step where we go to G and then we take the sign of G. We've mostly been talking about where we optimize some continuous function G and then we take the sign of it and we want that to match so yi. And this is in general the classification problem. And really, this is a supervised problem, means we have labels, and so we actually want to do cross-validation here. Okay, so this is important. That means we actually decompose X, Y into two sets, the train and the test set, and we're going to be doing everything over here. Actually, all the work we're talking about is just on the train set, but it's important to hold out this random subset called the test set, which we can use to evaluate how well this would work or measuring how well it generalizes. And this is because the ultimate goal, the real goal, is to generalize on so new data, and basically data that's IID from the same mu that XY is also from mu. So we assume that the data we got is from some distribution, and we want to generalize assuming we get new data from the same distribution. And the cross-validation goal allows us to kind of evaluate that and then maybe optimize by tuning hyperparameters that we haven't talked so much about, but we can tune them based on this goal. And this is something you can do with regression and classification, but for instance, could not do on clustering or dimensional reduction because we did not have the labels in those cases. Okay, so I think it's really important to keep this in mind as we're doing this. The solutions for the practice exam we will go over in class on Thursday. If we don't get to anything, you can find some past videos. Yeah, sorry. That's a question that was lingering. Okay, okay, so this is our goal here today. And we have been talking about, first we talked about linear functions for G, build a linear model for G. Linear G of xi always looked exactly like alpha, right, is just look like this. We had a coefficient 1 or actually coordinate 1, and then we took a dot product. These were the linear models, and this gave us this linear classifier. And then we talked about, with the extension of the perceptron, these kernel classifiers. So these all right, and we talk about these nonlinear kernel classifiers, and this is a particular type of nonlinear classifier. The other ones we'll talk about today are also going to be nonlinear, but they're going to take kind of a fairly different attack than what we're talking about here. And I just wanted to review a couple things and talk about kind of SVMs, which we didn't quite get to in the last lecture. And this is where we build a function g of x, which is going to have the following form. Let's just call this, we're going to assume that we, so we're gonna assume that this is taking the place of alpha because x is equal to 1. The first coordinate is 1 here, and so this we only need to worry about the normal direction. This is just mostly just simplifying notation, and we want to do this as an inner product here, but we're going to kind of rewrite this as the sum. We were thinking about this in terms of the perceptron algorithm, and then we had these alphas, and now we're going to think of this as this mistake counter, and we had yeah, and this was x. And so this guy is the same. This is the input x. I think I had written this as p before to make it a little bit more distinct. Okay, so those are all the same. I've highlighted there. Okay, and one thing we can do once we've written it in this way is, and so these, yeah, we use this now as the mistake counter in Perceptron, and this alpha is now an Rn over the n data points we have, and now we can replace this alpha I, yi with a nonlinear kernel in place here instead. Okay, so I can replace the linear function as a nonlinear function, and this this is now a function that I know how to optimize, at least with the perceptron. I could look at every misclassified point. If it was misclassified in a previous version, then I update alpha. I'd increment the corresponding alpha I value by 1, and this was kind of how a way to think about the perceptron algorithm. Okay, but what the problem with the perceptron algorithm is that it required the data to be so separable, and it depended only on the margin of the separation. And with a kernel, I said you can always get it so it is separable, so this was kind of okay. But the optimization in some sense was a little bit slow, because all I could do was increment alpha I by one of the alpha i's by 1 here. And these are these very long vectors. Remember, alpha was equal to alpha 1, alpha 2, up to alpha n. And so this was a long vector to kind of update. And one thing I'd like to point out is that when you update this, it's going to be mostly sparse. Most of the alpha j's are going to be equal to 0. Okay, and so we're going to start by thinking in this kernel version that, that in the, okay, so in the kernel version, that what you're going to do is the ones that are not sparse, non-zero alpha j, these are now going to be what's called the support, support vectors. Okay, if we remember in the linear case, okay, in the linear example here, we had this property that there was a max margin separator, and there are a small number of these interesting points that defined this margin here. Right, which is the kind of the minimum distance from the separator being green to the closest points that are classified correctly here. And these are called the support vectors. Okay, these pink points were called the support vectors here. They're supporting this margin. When I'm dealing with the kernel, with a nonlinear kernel, then basically any point that's non-zero is kind of going to support this margin. The margin is going to be defined as a function of any point which is non-zero. So the support vectors are not as easily defined geometrically anymore. I can think of them as any one that I had to update the mistake counter on. For the classifier, I've defined those are the support vectors, right? So I might get an example where alpha equals, say, 2, 0, 0, 1, 0, 0, 2, 0, so -1, right? These could also be, oh no, it's not, -1's built into the sum. Okay, so it's always positive values. Okay, then the support vectors here, these guys are going to be the corresponding indices here. This is I equals 1, I equals 4, I equals 7, and I equals 9. Those are going to be the support vectors here. It's hard to draw a picture. I'm in a nonlinear regime here. Okay, so then the support vector machine says, well, I could optimize it with the, I could optimize this with the perceptron algorithm, but I could instead say, well, I can say my cost function is going to be the I equals 1 up to n of some loss function of, this is going to be some convex function, where I write yi of g of alpha of xi here, right? And I want to, and this would be some overall loss function, but I'm going to write this as a function of alpha. And remember, my g of alpha of xi is now equal to the sum, let's say j equals 1 to n of alpha I yi kernel of xi. Okay, so now I can actually say, well, these are the functions I'd like to optimize over, and I only want to optimize, typically only want to optimize over the support vectors. Okay, so this alpha is now in Rn, but can restrict to the k, so support, so vectors. Okay, and I can write this as a cost function, and I'm not going to go through all the details here, but this will be a convex function if my loss function is convex, and then I can run gradient descent. I'm going to run gradient, so descent on h of alpha, and maybe restricted to just the support vectors. Okay, so how do I find the support vectors here? There are two ways to find these. I can find by just by start with the perceptron algorithm for case steps, or I just run stochastic gradient descent. If I run stochastic gradient descent, then a lot of these are, I'm only going to select points at random, and I'm going to optimize those. And especially if I do this with a hinge loss, okay, hinge loss is convex, and it has this property that, right, so this is 0, and the cost function of the hinge in this range, this is for the zi value, right, for this zi value, if that value is greater than 1, which means the point is well classified, well, then the gradient is 0 exactly. So if I do randomly select a point which is well classified, I don't update the gradient. So I keep this vector sparse. Okay, so I can keep the vector sparse even with SGD, especially with hinge loss. If I did something like the logistic regression, it's going to make a denser model. But with hinge loss, because it snaps the cost to 0, I'm actually maintaining the sparsity. Okay. Okay, and so there are, if you read the literature, there's a lot of other discussion about kind of looking at these kernels and thinking about support vectors in different ways. Some of it is useful for the understanding in ways. I think this whole holistic view hopefully is a little bit simpler view, and you don't need to get into all of, so much kind of scarier mathematics or notation that you get to describe this. The sum in G, yeah, okay, so this is the sum in G of xi be, okay, oh yeah, so these should be over J, yes, great. Yeah, that's the jth index, and this is it's a function. Yeah, so thank you, I misrepresented that. This should be xi, right? So let me try and make this a little bit more clear. Yeah, this notation can be a little bit confusing here. There's an xj and an xi. Okay, so yeah, so this xi is part of the input in the cost function where I iterate over all the things, where I iterate over all the data points I have in the cost function. And then inside of the function g, I iterate over all the data again, in order to build a model. So this is an n squared sort of approach, right? Instead of a linear approach. And one of the downsides of these kernel methods is they basically, if you do them the straightforward way, they scale so quadratically with the data size, where a lot of the other approaches don't. And so there's been a lot of work in the last decade or so of trying to make these more efficient, reducing this quadratic cost to something closer to linear. And there are techniques to do that we're not going to talk about in this course. But yeah, if it does look like there's a double sum here, that's because there is, and this is not happening in the other sort of approaches we're talking about. Great. Okay. So that was all I wanted to say about support vectors. There's some other stuff going on, but I think I'm going to move on to probably a couple of other classifiers at this point. Yeah, so let me just quickly start by mentioning kNN classifiers. And this is for k nearest neighbors. We're not onto neural nets yet. We'll move on to that next. This is kind of just to give you a sense of the scope of classifiers. This requires this uses some distance that goes. Let me write this as an uppercase D, so it's clear from R. Well, actually, you can define this in between the space where the data is coming from. Okay, and basically, I don't have to train at. There's like no there's no training here. Just so how I compute this f function, right, from xi, and this will give me a sign here. Okay, how do I compute this? I find the and actually let's write this as a p. So find the k is some parameter closest points x1 x2 to xk in x to the point P. Okay, so I can draw a simple picture of this. Okay, so if I have a query point here, P, I'm going to look at kind of the 5 closest neighbors in distance here, and then I'm going to vote on the signs. Then I'm going to vote. So, which sign is more so prevalent? That is the output. Okay, so in this case, query point P, there are 5 nearest neighbors. Approximately, let's pretend those are the 5 nearest neighbors, and 4 of them are are plus points, one is a minus point. So I'm going to make a prediction that f of p is equal to plus 1. This is going to be equal to plus. This is my prediction here based on the nearest neighbor. Okay, and if there is a good kind of classifier, if you ask for p near a bunch of plus points, it's going to predict plus. Near a bunch of minus points, it's going to predict minus. Okay, and in some settings, this is kind of, this works pretty well. It depends on how fast I can find the k nearest neighbors. It turns out in Euclidean data, you can actually do that pretty fast. People have worked on that problem for a long time, and there's some really optimized code. But you could also apply this if, like, my input was not Euclidean data, not vectors, but was like a text document, and I have a distance between text documents, right? If two of you turn in 2 homeworks and the 2 homeworks are very close to each other, there are metrics for me to know if they're too close to each other, you may have copied from each other. And so there are metrics for how to measure this, and I can if I have that, I can build a kNN classifier. I just have to do this, okay? So this is another type of classifier as part of this kind of survey of classifiers. Did I describe this in enough detail? Is this clear? Okay, yeah, so pretty, not too hard to think of here, and this sometimes works really well. A one nearest neighbor classifier has some really interesting properties, and sometimes works kind of surprisingly well. Yep, those metrics do work. You have to know how to use them, but those metrics on homeworks do work. We catch a lot of people every year for those things. They work especially well on code. The people who invented them are people who teach computer science coding classes, and they've seen lots of examples. Okay, it's not going to catch everyone, but it doesn't. To be effective, it doesn't necessarily need to catch everyone every time they do it. So, okay. I'm not particularly worried about cheating in this class at this point, but I just came up with a good example to mention this stuff in. Okay, let's talk about, networks. Okay, again, these are some of the oldest types of classifiers, and they're based on the idea of how, like, a neuron in the brain works. Okay, this was the original motivation. Kind of how they're used is strayed from that in various ways, in ways that actually make a difference in how well they work. They've tried to make them more like the brain, and those tend to work a little bit worse. Not to say that we should change how the brain works. That's how the kind of the biology of the brain works, but it's really based on how a neuron works in a brain. And the idea of a neuron, okay, is that, let me see if I can draw a picture of a neuron. It kind of is this object in the brain, and it has all these kind of these things coming out, and they sense like an electrical sort of impulse. There's kind of like a sensor on the end of these, and occasionally it will, so sometimes it will send a signal out. Okay, and the signal is gonna be like a pulse, right? Or it's gonna be it's either, kind of think of it like there's an electrical switch, it's either on or off. If it has certain, depending on what the signal coming in is, it either is sending a signal out or it's not sending a signal out. Okay, and so this is really kind of like a 0 or a 1. It's either signal out or it's not. And if there's some scale to this, but yeah, and or maybe it's like something between 0 and 1. There could be some scale quantity. But think of it kind of like a binary. It's kind of either on or off. Okay. So, and in fact, it's probably something like this. this is some function of the input, and this is the output here. This is 0, this is 1. And if the input is very extreme off to the right, it's probably going to send out a signal at the top, at the highest value. And if it's very far to the left, it's at the, it's not sending a signal. And if it's somewhere in the middle, it's ramping up, but it kind of ramps up, something like that. Okay, and what is it connecting to over here? Well, these are other of these neurons, right? And your brain is like this, is connected to these neurons. Some of these are connected to your nerve system, how you touch, you feel something, your nose, your eyeballs, right? They're all kind of absorbing signals that are sensing in some way, and they're passing through, and there's some decision-making happening inside this node, okay? What is this node doing? Well, it's kind of like accumulating something from each of these values and kind of adding these contributions up. Okay, so I can think of having x1, x2, x3 up to xk, right? There are some inputs, and these are, well, they're kind of 0, 1, but they're kind of like these in between 0 and 1. So each xi is, say, between 0 and 1. And then I'm going to somehow scale them. Some of them are more important. Some of these branches are stronger than others. This is an important connection. This is, I'm not sure about this connection. Maybe it's here, it's weaker. Okay, so there's some strength on here, on these branches. And some of them could actually be a value which is like negative. Could say if this is coming through here, alpha could be negative, in fact. Say if I get a signal from x2, that's a no-go. That means that's a bad sign, so I'm less likely to function on. Okay, so I'm going to have these alpha i's, which are going to be some real values here, some scaling quantity. Okay? And so then, this is basically going to be what's on the input here. So that means that this input is actually going to be something like the sum of I equals 1 to k of alpha I xi. This is exactly alpha x. It's a dot product here. Okay, so it's taking all these inputs and it's scaling them and it's adding up their contributions. And that's kind of what's going on in the neuron. And then it's making a decision. Okay, is this above or below a threshold? Do I turn on or not? Okay, so it's a linear model with some sort of thresholding function, or this is called an activation function. Okay, so this is called activation, so function. Okay, so this is how the neurons work in your brain, and they're all chained together in some complex way that we're, one of the big grand challenges of science right now is to try and figure out how to build like the full neural connections of a human brain, similar to how we did like the human genome. It's a much bigger challenge. Right now we can do things like the eyeball or maybe like a rat's brain, but the goal is to do it for a whole human brain to understand this structure. Okay, and a neural network is a kind of how to do something like this in a computer. Again, this looks like a linear model, and then there's something, this is a little bit different. It's not quite like the loss functions we saw, it's a little different. It's called an activation function. Okay, so we are kind of combining these linear models. This is like one key component here. This linear model is a key component. The other component are these activation function. Okay, and so this is somehow, it's usually going from real values and it's mapping probably to some restricted domain. Sometimes it's 0, 1, but there's some kind of changes or it could be -1, to +1, or 0 to infinity. There are versions of these, but it's somehow deciding an activation signal, and it's somehow restricting the domain in some way. Some popular ones are going to be so there's one called the sigmoid. This takes in phi of, let's call this as not quite a z value. Let's call this y value, and this gives us, it does 1/1 plus e to the -y. Okay, and so this gives a value in 0, 1, and this looks kind of like this picture up here in red. Okay, this will give a picture that looks kind of like the one in red, where it's mapping, it's trying to build a hard threshold. Do I turn on a 0 or off, or on a 1 or 0, which is off? Let's try and make it smoother. We're going to use gradient descent on the system to optimize it. So we want things to have a derivative. So if we just had a hard on-off threshold here, we wouldn't have a derivative. So this will have a derivative. Another common one is the ReLU. Okay, and this is it's like the hinge loss, but it's usually written as max of 0 and y, right? So this is in 0 up to infinity, right? And this one, the ReLU here is going to look like this, right? So this is like the ReLU. This is the so the sigmoid looks kind of like that. The ReLU is basically kind of like a hinge function, but it is depending on where it's 0 in both of these pictures. Say 0 is about here, right? So once it gets past, if it's positive, I'm going to keep the value, some value. So I want to, if it's larger, it's larger. That's great. If it's 0, then it's going to be so. But I don't want it to have a negative value. Okay. There's something else called the hyperbolic tangent, which is sometimes used at maps between -1 and +1. There are versions in here, but it's somehow kind of this activation function is important. If I just chain together a bunch of these neurons and they're just composing together linear functions, then this is not really doing something very interesting. But if I do a linear function and then an activation, which kind of is a soft rounding, and then another linear function, another soft rounding, and iterate this gives it a lot more kind of discriminatory power. And kind of it becomes more interesting when you chain these things together. Okay, so this is the basic idea. When we think about kind of a two, like when we structure this in a computer, though, okay, if this is structured in a computer, we probably don't just have this random connection of all these neurons floating around the brain. It's going to be more structured, okay? And you're going to have this this input layer, and this will usually be X in RD. Usually, you assume that you have data X, which is kind of a vector in RD, just like we typically talk about. Sometimes there's stuff you do before the input to get it in this format, and that's kind of a longer story we're not going to get into in this course. Okay, but you're going to then have kind of you can think of these in layers. Okay, and so this will be H1, and this will kind of be the output, and this will be in our what's the notation I use here? Probably let's just say RK. Okay, and I'm going to have an output here, And so what the idea is that I'm going to have, this is going to be have k values here. This same way I think of this as a bunch of these inputs. And I'm going to have a bunch of these outputs too, and they're going to be k values. And each of these values is going to have a kind of, it's going to have one of these neurons. Okay. Okay, what is this? It's a linear classifier with an activation function. Okay, then the neuron is going to be described, parameterized by f and phi, right? And it's going to be an activation function on top of alpha x, right? So this will be the output of the neuron, and so h, and this will be hj, alpha j, and alpha is itself an n-dimensional or d-dimensional object, and this will be activation function j, and the hidden layer, I'll say maybe the hidden layer 1, the value j is going to be equal to this, right? So for the hidden layer 1, this is a k-dimensional vector. The j, the value, is going to be a neuron, which is alpha j dotted with x, and then some activation function. Typically use the same activation function for everything in this layer, right? So let me instead probably say this is just going to be activation function 1, which I'm going to apply everywhere here. Probably the same activation function, and I'm actually going to have not just one of these neurons, but I'm going to have a whole bunch of these neurons. Okay, and each of the neurons is a linear classifier. Oh, and how do I, in the brain, how does your brain update, train a kind of a neuron? It runs something like the perceptron algorithm. On positive input, if it stimulates, if kind of a series of inputs stimulates something which is useful, then it kind of keeps doing it. But if it stimulates something which it didn't want, it'll send some negative feedback backwards, and it will decrease the weights of things that correspond with this negative input. So it runs a lot like the perceptron algorithm in some way. Okay, so this is one layer of the neural network. And so kind of a one-layer neural network is basically, if I just wanted to have one output, it's just you could run the perceptron algorithm, and this was the first way people modeled these. The next way they did this is they thought about these two-layer neural networks, H2 and K prime. And again, what this does is it decides for an activation function 2, and it again builds a kind of a set of these neurons. So this is like a fully connected graph, right? There's a lot of different connections going on here. Each of these triangles has a connection from everything, all the hidden values to the output, to the one output value, and those are kind of learned individually. This is for a fully connected network. There's some work where you don't always fully connect it for different modeling reasons we aren't going to get into in this course. There's a full course on deep learning. Okay, and people kind of figure out roughly how to train these two-layer neural networks, but there was kind of, they showed, well, you can't, learn all functions with this, and they were kind of a pain to train, and this was kind of the state of things about 20 years ago. People looked at about two-layer neural networks. Now, what is common is to have these deep neural networks, which is going to have like M layers. Okay, and sometimes you have them so they get, they'll get skinnier at some point, and then they'll expand back up again, and there are various reasons, to do this. And eventually, you have a single output, And this one is either kind of minus or plus 1, right? Eventually I round to, I take the sign at the final layer, for instance, right? And this would be the output. Okay. Okay, so this is kind of the structure of a deep neural network. It's a bunch of these linear things just chained together with activation functions. The activation functions are kind of needed in order to kind of do something interesting. And then at here, at the end, I take a sign function. Okay, just to do the final input. Okay, the full parameters of this model, well, there's the structure of the network. You've chosen how many things to put at each layer and which edges to connect in the model. Yeah, okay, so you need to design the network in various ways, and that gets into a variety of other modeling challenges we're not going to get into, but you're going to have a parameter set that is going to be kind of the alpha 1 through alpha k at layer 1, and the alpha 1 through alpha k2 at layer 2, and alpha km at layer m. And so you have a lot of parameters here, right? Some of these deep neural, the deep neural networks have millions of parameters that you'd want to set in order to do training on here, right? Okay, and so there's a huge number of these different kind of parameters. Think of if the size of the layers are all the same, then it was going to be, and each of these alphas is actually a vector, right? Each alpha is the vector describing one of the triangles, which is a neuron. That's a vector. And I'm going to have k vectors at layer 1 and another one at each of the layers. So it's going to be something like m times k squared if k is the same value. So, something like m times k squared, parameters. Let me just start over with that one. Parameters. Okay, so there's a huge number of these parameters, and you should worry, if you can train this, are you overfitting the model? The model is way more complex than typically the data. Turns out you typically would only want to run this if you have a huge amount of data, maybe not quite as many as you have parameters, but you want the parameters to somehow probably scale with the amount of data that you have. And the parameters may still be way more, a factor 10 bigger than the size of your data, and that might be okay with reasons we're still kind of wrapping our heads around why this actually works. Okay, so this is the basic structure of it, okay? And it gets complicated and messy, and it's hard to draw everything. And one of the reasons this has become popular is because, one, it builds much more complicated models than we're able to easily do even with kind of various types of kernels and polynomial classifiers. Okay, this can be much more complicated in various ways. And in some cases, that's good. Some cases, real life has complicated things. We understand language. We understand what captured inside of an image. It's really complicated how to decipher that. And so it requires a fairly complicated model. The other reason is we've gotten lots and lots of data. We've gotten really good at collecting data. We can train language models on the entire internet. And train image models on basically almost all the images not quite all the images on the internet, but lots and lots of images still. Like it's easy to take digital pictures. It was not so easy to do so when I was in grad school, for instance. It was hard to get all these pictures. So we have lots and lots of data. And perhaps most importantly is that there's a combination of being able to train these in some way, which I'll describe a little bit next, on GPUs. It's highly parallelizable, and it fits with what modern GPUs can do, which are highly processing computational cores initially designed for graphics, and then they realized, oh, the same sort of way we've optimized parallelism in a specific way can be tuned for neural nets. And now I think maybe more GPUs are built for neural nets than they are for graphics that they're meant to be processing. Okay, and those paired with software that makes describing this and deploying these fairly easy and straightforward. And that software is optimized all the things you need to optimize in it, so you really don't have to do that. To use them efficiently and smartly, you need to know how to set stuff up correctly and know what it's doing, what it's capable of. But the actual programming aspect of it has kind of been taken care of by this really nice, several very nice pieces of software. Things like TensorFlow from Google is one example. Yeah.
How does the accuracy of the neural network compare to like Perceptron? Because we're having like so much more cost, so much more, all these different bad things, but potentially overfitting. How does that like compare to Perceptron?
Yeah, so Perceptron, this is kind of, it includes Perceptron as part of the model, right? A Perceptron is like the tiniest neural network you could have. So so Perceptron is a very limited, you can think of it as, I've got kind of data, and it's even hard to draw an illustrative picture in 2 dimensions, right? These things are interesting in high dimensions, perhaps. On data that looks like this, there's no way Perceptron can do well, but there might be you could maybe feasibly say, well, there's kind of a classifier. Let's see if I've got these all on the right side here. That looks something like this. I don't know. Maybe if I didn't just have these 25 data points, but I had 25,000 data points, and they kind of fit this pattern of this green shape, well, then a neural network would learn that just fine. It would have no problem with that. And that's true even with it does things like when you're dealing with things like with images, understanding it. These multiple layers, and the different layers are capturing different elements. Like one layer, one neuron in one layer somewhere in this kind of 20 or 100 layer kind of deep network is capturing, is there a cat in there? Another one is capturing, is there a car wheel in there? That might indicate that there's a car, right? And then later layers are piecing these things together to do something. This is not by specific design, but these are properties that kind of emerge out of this through the training process in ways that when you first saw them, you're like, that is like so unexpected, so amazing. And then you're like, yeah, that actually kind of makes sense. That might be similar to what the brain is doing. It's kind of it's learning to decompose a problem into the important aspects in ways that the perceptron and linear classifiers, there's no way they could potentially do something like that. If you have enough data and you have enough powerful thing and you can train it, then some cool stuff actually emerges here. One of the other questions you asked is a great question, is they have so many more parameters than data perhaps. This seems like classic, like overfitting, right? We talked with cross-validation, what happens when you fit, like with polynomial regression. If you use a really high degree polynomial model, it's probably gonna fit through all the data, but then, or almost all the data, but it's too wiggly. It's trying too hard. With this, when you get past a certain kind of interpolation threshold, what tends to happen is these tend to start fitting better again. They have more flexibility in how to interpolate the data. And most of these actually basically interpolate the training data. Okay, but there are a bunch of tricks and things. Some are designed, some are kind of merged accidentally. They kind of tend to, the optimal ones tend to be simpler models in some way. And so if you interpolate and you're a simpler model, you tend to generalize well than if you're a more complicated model. And they tend not, there's evidence that they often don't actually overfit. They generalize, if you measure them on generalization error, right? I talked back here, I spent some time reviewing this, right? The goal is to generalize on new data for the same distribution. That's the ultimate goal. And these tend to do better in a lot of cases. That's why they become so popular, because they do better than linear classifiers. They do better than polynomial classifiers, and in some cases better than kernel classifiers. Not always. Sometimes kernel classifiers actually do better. Depending on the type of kernel and stuff you're doing, it can be easier to train. But they, and sometimes you can encode types of kernel classifiers as neural networks. And there's, you know, but like, for instance, there's another thing I'll talk about. I'll spend a little bit of time talking about the last like 10 minutes, like these random forests. Random forests are based on decision trees. Decision trees are very simple and interpretable, and random forests are, well, you apply a whole bunch of decision trees and it makes them uninterpretable, but they generalize extremely well and they can be trained easily. And these do better if your input tends to be, they can handle more general types of input more easily than neural network is. Neural network is sometimes important how you put the first stuff in the first layer, how you do that. And there's a lot of work in, well, I'm going to train a neural network, but maybe I'll do a separate training process to decide what to put in my inputs. So it's a little bit unintuitive. When I first was learning and understanding how well neural networks worked, I'm like, okay, the first few layers, and this is the way it works with images more or less. Images are a pretty standardized format. You just put all the pixels in. But the first few layers are kind of training the features, right? It's kind of putting these like filters, these local filters on the data that we used to hard code these filters on images. And then the first few layers kind of train those automatically. It optimizes all the parameters at once. And so the first few layers are learning to featureize, and then next few layers are learning to build a classifier or learning classifiers of sub-elements and then joining them together. But with language, it turns out it's important to kind of understand first the right representation of language. And so we train these things like these word vector embeddings, which then get passed often into the first layer of neural networks that do tasks on top of those representations. Now, how are those representations learned? Often, again, with some neural networks, but it's kind of a decomposed process in some way. And so that occurs in a variety of domains, but those are the kind of two most popular examples. Cool, yeah, okay, so this is kind of, this is what a lot of people are working on now, and this is kind of the big picture. One of the big reasons why this can work is because you can train a deep neural network with a form of gradient descent. In fact, stochastic gradient descent is typically what you would use here. But the point is, you can define and efficiently compute the gradient. Can efficiently compute the gradient, and the insight is that you have roughly k squared times n parameters roughly k squared times n parameters, and you don't do it all at once. You kind of do it by layers from the last layer backwards. And we do this by layers from the last, so backwards. Okay, so in order to compute right, so if you remember, we talked a little bit about computing the gradient, and this involved taking a bunch of these partial derivatives. And so for each of the parameters, we took a partial derivative that depended on everything else in some way. And this would, if you did this naively, it would be kind of a quadratic operation over all k squared times m parameters, which would be, it's infeasible, okay? You can't, that's not possible. It's very complicated just to write down, like you don't even like write down mathematically, you write a computer program that would do it for you, for instance, right? These are things you don't try and write down on a whiteboard, at least not on the full form. Okay, so, okay, but what you can do is you can compute the derivative of kind of the last layer. Basically, you're putting in, you think of, I have a, yeah, so the way to think about this is I've got these layers. Okay, and I've got this, all these things going in here. And so I'm going to put in an xi here, and it's going to run all the way through, and it's going to output a yi hat, this prediction. Okay, and just for simplicity, you might want to use a different loss function, but then for sometimes here you can actually use these for regression, not just classification. So just for simplicity, let's say that the cost function is the true yi minus the yi hat squared. Okay, so I've got some cost function, which is my error here. And if it's -1 + 1, or I say, is this a positive example or is it a negative example here? Yeah, this last layer is also kind of a perceptron here. Okay, and if I predicted it correctly, then the error is small. But if I'm thinking stochastic gradient descent, I can push one example through, and then I can say, what is I want to calculate the gradient with respect to this one example. And the parameters that are here, right? I have some alpha vector here. Well, I can figure out what those, I kind of stored, when I was going through here, I stored this value. I stored HM, the values in this last layer. And so I can compute what the gradient is for alpha with respect to the error at the end and the last layer in kind of these last alpha parameters. Okay, so I can compute the gradient with respect to this alpha in the last layer just using this kind of local neighborhood here. Okay, and then what I can do is I can push the output here into this last layer, and I can say what is some residual and the error everywhere in this last hidden layer, and then I can kind of do the same trick kind of for each of these neurons. Okay, and then this for each of these, I'm going to get this residual alpha m-1 kind of j, and then in order to, I'm going to propagate that into this hidden layer here as the sum of all of these terms. Again, it's linear, it's decomposable, and I'm able to take the sum of all the gradients from all these guys and add them up into this layer and push them backwards. So I'm doing one layer of the updates at a time. And so I can update all the parameters, okay? I'm not doing this a full justice, right? This would require several lectures to kind of get through all of the details here. But I just want to give you this main idea. This idea is called propagation. Okay, where I kind of take the error and I back propagate the error through the network because I've structured it as these layers. Okay, I mean, ultimately, you often see that this is written as as kind of this function, and you can actually write down all of the kind of, if I right, W1 is going to be alpha 1, alpha 1, 2, alpha 1, say K, where this is alpha 1, 1, alpha 1, 2. And I can kind of write this all as a matrix. So instead of doing a dot product on this guy in order to get this output, I can write this W. I can write this instead of a bunch of dot products, I can write this as a matrix multiplication. And I go from a vector to a vector, right? So what matrix multiplication does. And tensor flows from the idea, well, the parameters W1, W2 are, I stack matrices together, I get what's called a, what you guys call a tensor, okay? And so I can write this cost function in linear algebra as the last layer times the activation function at the last layer, and then kind of recursively m minus 1, phi of m minus 1, till eventually you get phi of 1 of w of 1 multiplied by x. Okay, and so you can kind of recursively write this down in this form. And each of these steps, the w is a linear operator, and phi is a differentiable operator. That's not linear, but it's differentiable. And if you write down the derivative of this, right? If you write down the derivative, you can do a partial derivatives through functions, and you basically start writing down the innermost thing and expanding to the outwardmost thing. And so that way of writing down the partial derivatives actually corresponds with this back propagation I tried to describe at a high level just before that, right? Where we're doing this, we're kind of figuring out how to update the parameters at the end of the model. And then as we move backwards in the model, we're updating the parameters earlier and earlier. But it is the right partial derivative. It is the right full derivative through these partial derivatives. Okay. Yeah. All right. Okay. So, I can I can try and write down some partial derivatives. I don't know how useful or helpful this is going to be to try and write down more math at this point. Yeah, maybe I'll stop here and I'll say something very quickly. I just want to mention what a decision tree is. And so this is like random forests are in like a lot of the world's problems, random forests work as good or better than the deep neural network. So I think it's important just to be aware of these. And so random forests, again, are just these compositions, a way of aggregating together a bunch of random perturbations of decision trees effectively. And random forests are uninterpretable, but decision trees are very interpretable. And you can describe these by a nice geometric picture, but they can handle all sorts of input here. And let me just try and draw a picture, I think, to get the main idea of what is going on here. Again, it's going to take input that is signed. Okay, and the idea of so the input data, X, it could be in RD or in kind of it could be categorical. And the thing is, it doesn't create like a linear combination of these features ever. So it doesn't ever combine features together at any step. So it kind of individually is building a classifier. It says, okay, I want to find a split. In this case, I've drawn it with only 2 axes here, okay? But you could handle much higher dimensions. And what it does is it tries to pick one axis and find the best really good split on this axis, where, say, a bunch of minus points are on one side and it's a less good split on the other side. And then it says, well, after that, I'm going to kind of find this other split, and it's all always these axis line pieces. So I'm not mixing together these components. So it makes it very general in the sort of input it can take. And then I might actually do here, because I get the bottom part is all pluses, and that works pretty well. And then I can also maybe split here and here. And I can think of these as kind of A, B, C, D, E. And this corresponds with an actual tree where I'm splitting at A, then I'm splitting at B, and then B has one child, which is, and that has a child, which is D. And there's kind of, if I make a decision, I actually walk down a tree. And computer scientists, you're all familiar with binary trees. And so it's doing this one coordinate at a time. It's not mixing the coordinates. That makes it very general. It makes you don't have to worry about mixing units and the other issues that normalization issues that causes. And the full optimum of these, again, is hard, but there are a bunch of kind of fairly good heuristics that people have worked that says, okay, I use some sort of information theoretic criteria to find the best split. And maybe I try all possible splits or a subset of them. Given one axis, I just have them in sorted order, and I just have to scan through them to find the one with the best split. So you can kind of optimize it in that way. And this is also interpretable, right? So a lot of the neural network model, in contrast, it's hard to understand what the classifier is doing. There's been a lot of work to say, okay, maybe this one neuron in the middle somewhere is identifying a cat, but it doesn't exactly identify a cat. It just kind of, you can generate a picture of it that looks kind of like a cat. So that's a good guess, or maybe there's evidence. But this one is pretty straightforward. I've made a decision based on this criteria, this split point, and then on a different split point. And so in terms of kind of explaining, these have been used to kind of build classifiers used in medical situations where like a physician needs to actually be able to understand what the rationale is behind it, because they want to make sure that there wasn't some anomaly in your data that the classifier was picking up on that didn't actually have to do with the true outcomes. And so these, you can explain to a physician why it's making, or at least how it's making decisions, and they can assess whether that's actually sensical or not. And there are trade-offs. These will not, decision tree by itself will not be as powerful as a neural network. It will not generalize as well based on the input and output data you give it, but it might actually work better in diagnosing what's going on. And what the neural network might be picking up on is secondary things that don't have to do with, say, some diagnosis, and you might not know about it. So it might be generalizing better, but it might be modeling some consistent noise in your input that isn't going to be when you use this in the future. Okay, so there's kind of a big debate of how do we assess the interpretability and the transparency of models, one, and this seems to be more transparent, but then how do we trade that off with how well it generalizes versus how well you can understand it? And this is an ongoing debate, and there aren't good answers to it, but kind of these are kind of two big points on the trade-off curve between these. All right, okay, well, we'll stop here. You guys have learned, we've covered so much cool material this class. I hope you enjoyed it. We'll get to review everything in class on Thursday.